Welcome back. Today it's my father's birthday. Happy birthday, Dad. October the 21st, 2020. All right. Um we're going to continue here on chapter 8 and we're learning about aromaticity. All right. So, question number 3 here says explain whether each of these species is aromatic, anti-aromatic, or non-aromatic. So we'll have to do a little investigative report here on how many pi electrons each of these species have, and comparing that to Huckel's rule. Also looking for sp3 carbons to define them as non-aromatic, and like that. So let's get started. So on A, let's do A. What I'm gonna do here, I'm going to write it down here on the right side for A, and you guys are gonna help me out. How many pi electrons? How many total pi electrons can you read? Well, tell me the pairs first. How many pairs can you read?
Is it 4 pair?
4 pairs, and total is 8. So we have 8 pi electrons. So is what? What is that molecule?
Anti-aromatic.
Anti-aromatic. Very good. All right. How about B? How many? Oh, this is a good one. How many pi electrons? How many pair of electrons that are pi can you read? Hint: if the electrons are on a double bond, they're stuck. Second hint: one of the electrons pairs in the oxygen is perpendicular, so it doesn't count. It's not aligned with the pi system. Hold on a second. I have interference. Give me a second. All right, you are allowed to talk now. Go ahead. How many pairs?
Is it 3 pairs?
3 pairs, yes. So there's 2. No, I'm sorry, 1 pair. Let's talk about pairs. 1 pair, 2 pairs, and one of them, one of the oxygens, is 1 pair. What is not a pair? This one over here, and one of the oxygens. So in total, this molecule has 6 pairs of electrons, which are, 3 pairs of electrons, which are 6 pi electrons. That makes it what? Aromatic. According to Huckel's rule, we have 3 pairs of electrons, of pi electrons, therefore is aromatic. Let me write down something here. I have here 1 pair of the oxygen is part of the pi system, the other pair of the oxygen and the lone pair of the nitrogen are not part of the pi system since they are perpendicular. So let's write that down. Okay, that is my explanation. All right, let's do C. What is C?
Is it non-aromatic?
Yes, correct. Why I had 54 participants and now 41. I mean, jeez, man, you guys have to stay in class. It's not time to sleep. Yes, so there is an sp3 carbon right there, so it's non-aromatic. So there is an sp3 carbon, so it's non-aromatic. Excellent. How about D? How many total pi electrons do you read?
3.
3 pairs. Excellent. So there is 6 pi electrons. So it's what? Aromatic, right? So one note here, one pair of the oxygen atom is part of the pi system. The other one is perpendicular, is away from the pi system, so it's not part of it. All right. Okay, let's do E. Who can solve E? What is E? And why? Anybody?
Would it be non-aromatic?
Yes, it is correct. Why is that?
Because of the sp3 carbon.
The sp3 what?
Nitrogen,
Yes,
sorry.
yes. Okay. Yeah, the other carbon, right? Yeah, the nitrogen. Very good. Who was that answer?
Ashley Cannon.
All right, Ashley. Good job. The nitrogen, you're awake and alert. So the nitrogen is sp3. Check this out. That nitrogen has 4 directions. So that's an sp3 nitrogen. So, or thus, it is non-aromatic. How about D? How many pairs of electrons can you read?
5 pairs.
5 pairs. Exactly right. That's a total of 10 pi electrons. So what is it?
Is it aromatic?
Let's put a condition here. So it's aromatic. In parentheses. What do you think will be the condition here? Like it's fully conjugated. Most likely it will have a full HOMO. And let's see, it's cyclical, and it needs one more condition that we don't know of, because the tether, that cyclic structure, is big. It's almost like a pizza dough. So unless that is perfectly flat on the tray, we will never know if it's planar, right? So it needs to be planar. If this molecule happens to be planar, then yes, it's aromatic. If it's non-planar, then we'll say it's non-aromatic. All right, but we don't know that information. Okie dokie. Any questions up to this point? This is your chance to ask questions here.
For part E, so it doesn't just have to be an sp3 carbon, it can just be whatever species is in that ring.
Yeah, imagine if you had this thiophene that acts like an oxygen, that's sulfur. So yeah, one lone pair will be out. Oh yeah, that's not a good example. This is an example that is equivalent to oxygen. My bad. If it's phosphorus, then if you have something like this, let's say you have that. Oopsie. Yeah, that's equivalent to that. This phosphorus here will have 4 directions. So I think it's hypervalent, so it can handle the plus. I'm not sure. But yeah, exactly right. This we said it was an sp3 nitrogen. So this one is an sp3 phosphorus right now. Probably has a lone pair. Maybe not a good example, but I'm not sure. So anyways, I was just trying to pull another atom that was underneath nitrogen. Maybe phosphorus is not a good example. Never mind, because it's hypervalent. But yeah, so because this nitrogen has 1, 2, 3, 4 directions, it's sp3. So it's not planar. All right. Now, if you have it like this, check this out. What if it's like this only? You think that's aromatic without the plus? Right now it's trigonal planar. That is an sp2 nitrogen because it's in conjugation with a double bond. In other words, we're going to learn. This is in my recordings. If you have resonance, then you go from, it looks right now like it is right now, it looks sp3. So let's say it's sp3 because it has 4 directions with a lone pair, right? But if you can do resonance, and it can, check this out. Now this nitrogen is what? sp2 hybridized. So in choosing if it's sp3 or sp2, you have to say that carbon is sp2. You choose the lowest hybridization. Yeah, I think I mentioned that in my recordings when we were talking about resonance and hybridization. And if I didn't, well, let's learn it now. Yeah, that's how this goes. Now, this molecule, it still has 3 pairs. So it's aromatic. Here you have 3 pairs also of pi electrons. All right, so this fits. All right, let's do number 4. This is a word problem. It says 2,4-cyclopentadienone, this one, it's unstable and cannot be isolated, whereas 2,4-6-cycloheptatrienone, this one, is quite stable and is readily isolated. Use arguments based on resonance and aromaticity to explain these experimental observations. Hint: recall a resonance structure that is commonly written for the carbonyl group. Basically, I told you everything here, even though you might not see it. But the hint really throws this problem away. So starting from that hint, I'm going to look for the resonance structure and then find out from it why the molecule on the left, it's stable. Stable means it will be aromatic, right? Because I don't see any sp3 carbons. And unstable means it will be anti-aromatic. So that's what we're going up against here. So this is a 7-member ring. I go draw my 7 carbons there. This one is easy. I just had to draw 5, like a home plate almost. No, the pentagon. All right. Then I'll keep my double bonds where they are. And here's the thing. So you have oxygens with 2 lone pairs each. Now, one resonance structure for this carbonyl will be taking these 2 electrons and moving them up. So in total, I will have 6 here now, with a minus charge and a plus right here on that carbon. Same thing for this one. These 2 electrons, I'm going to move them up. And that will have a minus charge and a plus right there. So basically what we're doing here is, okay, we have a carbonyl, and we said before that a resonance structure, because this is partially negative and this carbon here is partially plus. Remember that we did this before? We now say with confidence that these 2 are equivalent. All right, where this carbon here doesn't have a full octet, so it's plus. All right, so I think I can solve for this thing now. Check this out. How many pairs of pi electrons can you read from this molecule? Pairs.
Would it be 6 pair?
It will be 3 pairs and 6 pi electrons. So let's try to get that right. 6 pi electrons, and you had the right idea. Is it aromatic or anti-aromatic now?
Aromatic.
Excellent. It's aromatic. Awesome. How about the one on the right side? How many total pi electrons do you read on the ring? The oxygen is far away. Notice the oxygen is not contributing to the resonance structure of the ring and the number of pi electrons. So this is 4 pi electrons total. That means it's anti-aromatic, right? And now you can say with confidence that this is the reason why this molecule right here, or the one on the left, this one, is stable, it's aromatic. So on the energy levels, aromatic is lower than non-aromatic, and then the highest is anti-aromatic. All right, very good. Let's do the next one. You'll do the similar thing. So let's see, let's find out first what this problem asks. All right, let me delete that. Coumarin is an important natural flavoring. Explain whether the oxime-containing ring has any aromatic character. All right, let me tell you a little bit, little commercial here. We have a minute. Coumarins are very popular compounds, and they're heterocyclic compounds. One of them is warfarin, and warfarin is used in supplements in small amounts, like diet supplements. In small amounts, they make your heart race a little bit. But in higher quantities, it could make your heart go too fast and eventually die. So when I did my master's at West Virginia University, this thing happened after I went there. No, before I went there. I worked for a professor there, and he told me the story. He said that one of his research students was working with warfarin, and he started eating it in the lab. And so one day they found the dude died in the lab from eating warfarin, which is a coumarin. And yeah, it was a big thing there. Ambulances, fire trucks, police cars, everything. It was like chaos, he said, because the student poisoned himself with warfarin. Pretty sad.
Wait, why was he eating it in the first place?
Well, he knew he was developing it, right? So,
okay.
So he knew, though, that it was a supplement for, people take, you go to a GNC store and you want a supplement to like help you boost your stamina. So warfarin, warfarin is there. It's one of the, so the dude, he was testing it out on his own body to see how much he could handle it. And I guess he just was tempted one night. It was very unfortunate. Yeah. And he took an overdose. Apparently he was doing it for a long period of time. That's what the autopsy said. Pretty sad story. Very brilliant guy. He was actually a postdoc, I think, working on this project. Young life that was washed away by a coumarin. All right, so I'm gonna solve this problem next time when we meet, and you will remember this story when we talk about it. All right, hey guys, have a wonderful day.
Do you have any office hours right now?
I do, yes. Let me